missed it.
calculus and like a reporting arts class.
Oh,
It's in the calculus.
yeah, that's right.
You doing it?
Yeah.
Nice.
I'm excited now.
What you excited about?
Calc 3 class.
Yeah, we're gonna have an awesome time. Yeah, I'm gonna try to actually make it. I've asked the physicist what's important because a lot, like when I first started teaching Calc 3, when I took Calc 3, we went to places that classes didn't go, like all the way to Stokes' theorem, like really deeply into that. Have any of you had Calc 3 here?
Yeah, I did.
Did you get to Stokes and Greens?
That was a while ago.
Yeah. Did you, Josephine?
I did, but I don't know. Stokes' theorem sounds familiar,
Yeah.
but I don't know.
Yeah. Yeah. Flows.
I think
Flows and stuff.
Oh, I think we got there with cyber 2 semesters ago before it was a good question. I think so.
You what?
I got there with cyber before I came to your not numerical, your DiffEQ class.
Oh yeah, yeah. Yeah.
We did that together because I also had Dr. Cyber.
He got you to the doorstep of Stokes. I better get these notes out. I pretty much know what we're gonna do. I completely know what we're gonna do because I throw my pens everywhere. My God, this is a crazy shit show. It's all right. It's a-okay. So you might have an assignment for me today. Is that correct? And I have one for you that I'll get you by Wednesday.
Another one?
No, I have to grade. No, not to give back to you.
Oh, okay.
Anybody got this? If you need till Wednesday, just that's cool.
Again.
That's so good. Thank you. Thank you. Anybody got this? If you need Wednesday, I'll take it. I'm late on getting stuff back to you.
Is that your class?
You're late on getting stuff to me.
Your junior registration.
That's crazy. I'm on campus for one class on Tuesdays and Thursdays.
Yeah, that's nice. You do. Have you had Friday classes every semester?
Yes.
Damn.
That's what I heard when you're a physics major. The classes always go on Fridays.
I think my next semester is the first one without a Friday class.
Until like you're totally catch up, but you can just come to class.
Oh yeah, yeah. I haven't started doing that yet. Yeah. At some point, I may reach that.
Yeah, that was like, oh, actually, that's not true. Dude, I was just trying to find a free copy of the book.
What's up, dude?
Oh, I was trying to find a free copy, an online copy of a book, and instead I found the answer key, and I was like, that's really helpful.
That's really nice. Yeah,
Like,
you're good
wow.
at that. You're good at finding those PDFs. I'll let you find them first, test them out on your computer. Oh, is that for me? Thank you. Many thanks. You want to hold it?
Don't say
It's
that.
tomorrow.
Don't say that.
That's no rush part. Hey, could you do me a favor and use a single trapezoid to approximate that area and write the formula out for me? Yeah, yes, you can, Alevina. We don't want to have negative attitudes on a Monday. We got really, really cool stuff today. And I'm just introducing a little nomenclature. H is the width of the original interval. So you kind of like know it, or you have to look it up, right? One of these two, I'm thinking. Or you're just waiting for me to write it up. That looks like about 70% of folks. 30% of folks who might know. What do I write here? Anybody? I see that Lou has it. Lou, just tell me what you
Oh, okay.
We won't torture anyone.
Well, so like to start, I said it was 1/2 times the height times f of a plus f of b.
Yeah, beautiful.
And then I just factored some stuff.
Nice, nice. And that's about all we can do here, right? Because we don't know what f is, and we don't know what h is. So this is the simplest way we could approximate, and it's a pretty good approximation. Does anybody remember the order of error on the trapezoidal rule?
B minus A cubed over 12.
Yeah, so I'm actually, what I'm thinking, Christian, is the power
Yeah.
on the remainder here. 7, 6, it's
Squared.
2. It's 2. The rule that had order h to the first, that was the rectangular rule with just the midpoints being used. But then this formula, and I think we looked at one other method, where we use trapezoids as the top, Simpson's rule. That was still also order h squared, but this one's cake. This is such an easy computation to do. So now let's try to do something interesting here. I'm going to introduce the notation that makes sense today, but did not make sense on Monday or Wednesday whenever I was putting gobbledygook about y sub 1 halves up and stuff. We're going to call this x0, we're going to call this x1, and so this first y value is going to be y0, that's the leftmost y value, and we're going to say y1 there. And the reason we're using those subscripts like that is because I want to use fractional notation. So if I'm halfway across, it would be x sub 1 half, 3/4 of the way, x sub 3/4, so forth. Makes things nice for this. And everything today is going to be powers of 2. And that's going to make some really beautiful things happen. So the first thing I'm going to do is say, let's just pick the point right smack dab in the middle. So this point here, we're going to say x sub 1 half, and that is actually, b plus a over 2. That's the average of those two, right smack dab in the middle. And so its corresponding y coordinate is y sub 1 half. All right, now let's use 2 trapezoids, and I'm going to write this up because something really cool is going to happen. So let's just do the raw formula first. We're going to call this T2. This little subscript is the number of, it's not the number of panels, but let's just hold off. We'll call it T2, and then I'll make sense of that. So this first one, I'm going to have a trap here and a trap here. You know them very well, so now we're on first name basis. I just call them traps. Let's find the area of this one plus the area of this one, and just write that out. So what is the base going to be now, though, of the trapezoids? What is their base?
H over 2.
H over 2. It's the original. Yeah, exactly. So it's going to be 1 half times h over 2. And then I'm going to add them together. And they're each going to be 1 half height times the sum of their altitudes. So for this first one, we're going to have just y sub 0. That's this side. Think about this middle one. It's going to participate in the area of this and this. So I'm going to actually add it in twice. So I'm going to have 2 y sub 1 half. And then I'm only going to see that right edge exactly once. Let me stop for a second to make sure you see where that's coming from. And that 2 is because of the shared height that they have. If you were to break this apart, you'd have y naught plus y 1 half, and then y 1 half plus y 1 as the 2 separate areas. Is this making sense? Okay, cool. So let's do a little bit of finagling here. I'm going to actually just make a little note on this thing. This thing, we could write it using this y notation as 1 half h y naught plus y 1. Notice that that is still here in this formula. In fact, I'm going to pull it apart. So what I've got is 1 half times h over 2 y naught plus y 1. And I've still got this piece here. So that's going to be 2 times a half. Those cancel, h over 2 times y 1 half. Make sure that looks good. Once we get this couple steps into this, you're gonna see, and you're gonna be able to catch the rhythm that's going on here, because it's pretty shocking in a way. It's kind of weird. Does this look okay? Let me stop. And make sure it looks okay, just because, you know, I'm a fry baby. And sometimes things fall out of the skillet. Whoever says that makes. We good? Any questions? Okay, cool. So look. This is actually T1 right here. So T2 is 1/2 the T1 estimate plus h/2 times just the y value of the new point. So notice this is the new point. And now we're going to cut this into quarters. So I'm going to take the half point of each of the existing subintervals. So for the next one, in T3, I'm going to have x 1/4 of the way across and x 3/4 of the way across, and then those corresponding y values. And we're going to use 4 trapezoids. So our next one, this is going to be y 1/4. This guy right here is y 3/4. And let's do, take a minute, find the area of those 4 and see if you can find a similar rhythm here. Look for this T2 in it. So it's going to be, here's a little hint, it's going to be something T2, and that's going to be 1/2 T2. See if you can figure out what the ... is. Because then we've got it. Once we see this, we've got a good rhythm going. But the way to do this is to first just kind of write out the raw thing here. You're going to have h/4 as your base for each one. 4 of those. We won't do this again, because I think we can kind of make a leap here, an inductive leap. Anybody care to summarize this? Like if you were telling someone, you're tutoring someone, numerical methods, what would you, just how could you say this in a simple English sentence? That to get from the current level to the next level, what do we do? Sure.
So you can say like you're taking 1/2 of your like current T, and then you add your current like height distance, right? So like our current one is h/4 times the quantity of our added in heights.
Of the new points. Yeah, exactly. So thank you. Yeah, so at each point of the way, we're taking 1/2 the previous trapezoidal estimate plus the current base width, essentially, the width of however many we're at here. So that's h/4 because I have 4 panels right now. And then just the sum of the new y values. So let's see if we could get crazy. So now that we have a sense of what this is, what would it look like for T4? Do it without drawing, without thinking, what is T4 gonna look like? This is our math, now we're doing math jazz, right? I think I saw Josephine check to see if I was recording already. Yes, thank you. I thought, yes, I appreciate you. Good. Yeah. Notice how it's the odd multiples of an eighth that I added in. Here it was the odd multiples of a quarter. Here it was the odd multiple of a half. There's only one of them in that range. So beautiful, such a beautiful pattern. Each one of these has order h whatever. So for example, so T1 had order h squared, error. T2 had order, now the h was cut in half, but it's still a squared, but it was h squared over 4, error. T3 had order h cubed over 8, error, and so on down the line. So that order is, oh, sorry, I don't know why I put cubed, excuse me. Squared, and then, yeah, so it was 2, 4, 16, yeah, 16, thank you. But they're all order h squared. It's just the h is getting smaller as we move down the way. Let's keep this in mind for something freaking awesome that's going to happen, but let's do one example first of the trapezoid rule so that we have a little table that we can rock on. And I don't know, somebody give me a cool integral. Let's do, yeah, somebody give me a cool integral. I've got like a bunch of them. Like, you never get to come up with the integrals. What's that?
Got a weird one.
You want a weird one?
Yeah.
All right, let's do it.
Is it fine?
What is it?
I do e to the x minus 1 over e to the x minus, or not in the power, but e to the x and then minus 1.
Okay, cool, like this.
That one's to the power of x minus 1.
Okay, like that?
Yeah.
And then, like that?
Yeah.
Okay, I like that.
That's really weird.
I like the
That's
beautiful
nice.
rhythm. That's
Yeah.
nice. It's very nice. Let's see, can we do a little bit of,
It's just like a straight line in the middle of nowhere.
I'm gonna do a quick tweak on it, just to like
Yeah,
make it, yeah, so we're gonna do this, what range? We gotta be careful because we don't want the bottom to equal 0, so we wanna avoid e to the 0. So maybe to the right of it, would that be okay?
Yeah.
So let's say, because we don't want improper integrals, those are verboten. What's that? Did you say natural log of 2?
No, no.
Okay, I was like, wow, man, you had a lot of coffee this morning. Let's do 1 to 3, just because it makes division of the interval a little bit nicer. Let's make it 4. Let's make it 4 units, so 1 to 5. There we go. Cool. All right. Holy shit. So, let's start off with the basics. So our function, f of x, is, oh, and I did want to, I'm going to pull the e to the -1 out in front. So it's e to the negative first, integral 1 to 5, e to the x over e to the x minus 1 dx. Just so we have one little less thing to do every time we compute that value inside. And, all right, so what will your turn. What's T1, calculator, squad? Excel squad. If you want to pull out Excel, that's a smart move. Nothing wrong with that?
It's quite the thing to calculate.
So,
It's quite the thing to calculate.
yes, it is. Creator, yes, Dr. Frankenstein. Yeah,
It's pretty awesome.
I like it. I would have never thought. That's why I wanted you guys to do it. So I wouldn't have thought of that. I would have done some stupid
I
sign.
can't remember this stuff though, exactly. In my head it's like a somewhat different. Cause I did graphics earlier because it looked really funny.
Oh, really?
Yeah. There's like in the middle of it, there's like a huge gap and there's just like a weird line. Just like,
Well, maybe I'll try to sketch it. Well,
nah,
I will. I can't. It sounds fun. It sounds good. At least the X values are going to be nice. Can't say much for the others. Now let's just see here. So what is our age? 4. I guess, shit, still want that E to be part of it. Or do we want to just multiply our, what do you want to do? Do an approximation of that or include that in the approximation? You know what I'm saying? Do this and then multiply by 1 over E. Daniel, what do you want to do?
whichever one's easier for you.
Whichever one's easier for me.
Whichever one you think is easier.
Yeah, shit, I don't know. Let's just fucking put it back in. Sorry. There we go. Yeah, same, just the same damn thing. Sorry. Same shit. Do this guy here. So let's see, so when we're at 1, that actually turns out pretty nice, doesn't it? When we're at 1, so this is, I'll just make this X. Oh, 1 over, pretty. Yeah, it's about as easy as anything, right? Alright, I don't have my cell phone with me, so I don't have my calculator. I have to, wait a minute, where's your calculator? It's my phone. You made this? What are you doing? Get this.
What? Wouldn't it be 2? Why are we multiplying by a quarter?
It should be,
Wouldn't it be
1
2?
Yeah, it should be 4 halves, right?
Yeah.
Yeah, that's H
Okay.
over 2. Yes, I did that wrong. Thank you.
Okay.
That's good. Good stuff. Did you get this worked out, Lou?
Not yet.
Okay. You're just busy finding my flaws.
Oh yeah. I was just totally. I was trying to not do this. I wanted Daniel to do it because he picked such a freaking awesome.
I think we all feel this way.
Let me get my computer out. and do it.
Yeah, and
I won't type it on my
he's
phone.
basically like, you
Just watch
guys
it
do
hand.
it.
It's fun,
So,
that's
you
right.
just find the value.
Yes.
Okay.
Yeah, it looks like you kind of did it there. Is that 1.9047? Okay. Let's see if anybody else gets that. We'll put it here. It gets easier after this because we just have to add in some things. The boot up is this step. And somebody let me know, that was Ms. Labina's. I have great faith in her. Labina, how many, so let's go out a couple more decimals, just,
Okay.
do you have it recorded or not?
I went up to 5 decimal places for my value.
That sounds good.
They gave me 4 back. I don't know where that was.
Okay. Was it a 0 maybe? And it-
Probably, yeah.
Okay, cool.
Take again.
Take that, until somebody tells me different.
I got it.
You got the same thing?
Yeah.
Was it 90470?
Yeah. And then I got a 3.
Cool.
If you want even.
I kinda do, just to have it in there, yeah.
Okay.
Thank you. Cool. So that's probably a pretty lousy approximation. We don't even know the truth yet. We could go to Wolfram, but we don't need Wolfram. We've got numerical methods and lots of time. So let's do T2. So this is 1/2 that estimate plus, now what am I gonna have here? I'm gonna have h over what? What goes here? Is it 4 or is it a 2?
Because aren't we like multiplying with the new divisions, if that makes sense?
That's not, isn't that a music group? Hold on. So it should be 1/2 the previous h. Yes. So it's actually just h over 2. So again, it's a 2, I think.
Yeah.
Yeah. Because look at the formula. This was h over 2 here. So,
Oh, yeah.
yeah. Does that sound right?
I was mixing up my y and x coordinates.
It's all good. It's so easy to do. And then I just have to add in the value of this function at the midpoint. And that midpoint, let's see, so what we got? Here's 1, 2, 3, 4. I actually have to draw this out to figure out where it is. 3. So this is going to be f at 3. Right smack dab in the middle. What do we get for that? Did you get some?
Huh, no, I'm
Oh, okay.
I am both trying to get through it, but also thinking how I could make it like iterable.
Yeah. Well,
Yeah.
we do have that. Shit, I wish I had my calculator so bad.
Do you want one?
Yeah, thank you. That'd be great. Thank you so much. Well, that's like a real calculator. Nice. They still cost exactly the same as they did when the space program was in place, like,
Probably.
but even though it cost them like 5 cents to make one of these days. Well, Lou, there, just that's the on button. Okay, got it. Thanks. So, I'm gonna do this part first. So I need to write it out. It's gonna be 1/2 of that beast plus twice e squared over e cubed minus 1. And good lord, where's the freaking e? Oh, why do they make e second? Isn't that odd?
Yeah.
It doesn't. Yeah.
I don't know. There's a lot of interesting choices.
Yeah. Agreed. And if anybody gets this before I do, please shout out and stop me from my misery.
I think it's 1.726. Is that what you mean?
Yeah.
1.726
Yeah.
for the whole thing, or the just this?
The whole thing.
For everything.
Okay, cool. So 1.726. Can I have a just?
I got 3 6s and then a 1.
Woo. Okay. Ooh, that's nice. Nice. Is this looking replicated anywhere? Awesome. So that's our second estimate, honing it in. And I'm thinking, since that estimate went down, it feels like the original must be kind of convex like this. Because if it was concave, I would think we'd just go up. You know what I'm saying? So if it curved down, you just have more trapezoids underneath, giving you more more area. So let's get a couple more out here. Let's do T3. That's going to be 1/2 of 1.72661 plus. Now I'm going to keep cutting this in half. So every time you move down, the number in front of these little tag-ons goes halved. And then you're going to add in f of 2 plus f of 4. I'll try to do this. I cleared out a bunch of stuff here, Lou. I apologize. Is that
totally
okay?
cool.
All right, thank you.
Yeah.
What is this? This is first square. Got there's that Beyonce song that people are dancing to, Diva, that song, that dance, you know what I'm talking about? No? How can you guys not know this?
I also live under a very comfortable rock, so.
It sounds lovely.
There's a shocking amount of things I don't know about. And a shocking amount of things you do know about.
Oh.
Specific interest.
We won't ask, it's all good. I think I'm starting to almost figure out how to use your calculator, Lou.
Oh, okay. I'm glad that it's going well.
It's actually not. It's actually not going on. Like, how do you delete just a single entry?
With the delete.
There should be delete on.
Oh, okay, got it.
Delete
Cool, thank
here.
you. Yes, somehow that makes sense.
Okay.
Yeah, that makes a lot of sense. Thank you, sir. And then we've got the square. Quite painful to use this. I feel like I need to do one of these instead of just making y'all suffer. That's on the fourth.
This is what I didn't think of before, but it would have made this a whole lot harder.
This I
Is that-
got
I don't even know what that is.
0.800202166 just for that.
It's like a multiplicity equation to the power of e.
Is that e to the x factorial?
It is e to the x factorial.
Whoa, why are you doing that? Aren't things bad enough here?
No, it's the original equation I thought of that I didn't think of in time to give you.
Okay, okay.
I'll show you what it looks like.
And I
It's
think I
really
lost the 6 there because Josephine told me 3 6s. And I copied
But it's
over.
not perfect. I had it better.
Okay,
It's better.
1.6635326 rounded up.
You put this
Three
an
to
extra
six.
6 in there.
You got Josephine, did you get
Huh?
that?
I got a number, but I don't like it.
Oh God.
I
Okay.
don't know.
What's your number?
3.2.
That seems that seems too big.
This is what I got. 1.6635. Okay.
Cool. Okay. That's
I think you
Yours just has an
have
extra six,
one
right?
extra 6 in there.
Yeah, it should be 2 6s.
Yeah.
Should there's only 2 6s?
I think so.
Correct. Yes. Thank you. Josephine, I can come take a look.
It's okay, I'm probably just in parentheses hell, so.
Yeah, they can. Yeah, fair enough. All right. One last one, you know.
Oh.
Yeah. God, let's not actually.
No, let's do it.
I'm
Oh,
almost
yeah.
done with it.
Okay, let's fucking do it. It's only 4 new points with terrible coordinates. And don't forget, now we're gonna have a 1/2 in front of that sum of new points. So it's f at 3/2. Yep. This is why Excel would be nice.
Oh my gosh.
Yeah. Thanks, Daniel.
Yeah, could have been worse.
Could have been worse.
It could have been
worse. I could have
This
used
is what I was
like.
thinking of.
Oh wow. Oh, that's cool. Yeah. That's really cool. You should.
Sorry, I put an equal sign 1 divided by 8, and it was like January.
Can you define functions on this thing? Probably somehow.
I don't know how to do it on that one. I can do it on my other one.
I don't know.
But I might have gotten it.
You got it already? You already got
On
it?
Excel.
Oh, what'd you get?
I got 1.644599. I don't know if anyone else.
Okay, well hold on to that. So it's 1.644.
2 4s. 5, 9, 8.
Cool. That's.
I don't know how far you want to go.
Oh, that's plenty.
Oh, okay.
That's just hunky dory. I think we're starting to get the sense that this integral's probably 1.6-ish, but we'll know better in just a minute. Anybody else got that number? We're not doing any more after this. We're going to just take these and improve them drastically with some simple moves. We're going to Richardson this stuff. Oh yeah. And it's crazy. I showed this to Dr. Gray this morning. He was floored. He was floored. He'd never seen this. Are you skeptical of that, Josephine?
No, I was thinking about the Kool-Aid Man.
Okay.
Because you were like,
What?
oh
yeah.
So I just was like,
All right. I need someone to just record those 4 numbers.
Almost got there.
You almost got it?
Oh, what? I got them all on Excel.
Cool. Beautiful. I
Awesome.
want that. So is everybody okay with this process? That's all I want. I want you to
So
just be able to do this.
It's a beautiful equation.
What's the actual? Is there any questions on how we did any of
Actual is
that?
like 1.636.
You got the.
I want to get it on some
So-
I didn't watch the video.
Yeah.
Oh, it's
Maybe
okay.
if we
This
did
is
it like
this is
3 or
oh
4.
got it.
We get that.
Easy peasy.
Yeah, that might be. You might. Yeah, it's okay.
Yeah.
As long as you
Look
can.
at this.
This makes sense, assuming you knew the trapezoid rule, or you could. Yeah. Okay.
I can backtrack.
It's pretty easy. You
So
got it.
nasty.
And if you need help, just let me know. We'll go through it. Okay. So all these approximations have order h squared error. We are going to use Richardson extrapolation to bootstrap up from these 4 estimates to one estimate that will have order h to the 8th precision. So let's do that. You got a question? No. Okay. So let's just talk really quick about a very special version of Richardson extrapolation. And it's this case where the h's differ by halves, and it makes things very nice. So remember, recall, if we approximate a quantity g, so this is the true quantity, using formula little g of h, and h is a step size. So this formula, this approximation, depends upon this step size h. Then if we also approximate with step size h over 2, i.e. we get this formula, we take our formula, we replace the h with half the original h, so that's g of h over 2. We can Richardson extrapolate these because this formula right here, suppose this is an order h squared approximation. We could do this in general. I'll just do that. Okay, no, put a little p there. Just put a little p. It'll just be easier. Because we're gonna have to use other things besides order h squared in a minute. So the Richardson extrapolation value is going to equal step size 1, which was h to the p, times the estimate at the other step size, minus the other step size to the p, g of the first step size over, and now on the bottom I'm going to have h to the p minus h over 2 to the p. That should look kind of familiar. But it's going to be really pretty, and we can simplify quite a bit here, because this is actually h to the p over 2 to the p, h to the p over 2 to the p. So what I could do is divide the top and bottom by h to the p. Notice you can pull an h to the p out of here, out of here, out of here, and out of here. So cancel, I'll just put a note here, h to the p. And there's no more h's now, there's just powers of 2. And what we're going to get here is no more h to the p, just g of h over 2 minus 1/2 to the p, g of h over 1 minus 1/2 to the p. We're gonna make that better too, because those fractions are nasty. So we're gonna multiply the top and bottom by 2 to the p. So multiply by 2 to the p over 2 to the p. And what we're gonna get is 2 to the p g of h over 2 minus g of h over 2 to the p minus 1. This is going to get us everything we need. Just thinking about how that trapezoid rule worked, every time we got a new estimate, we had h over 2 from half the previous h value. So this is exactly what we need if we're going to extrapolate. Look how beautiful that is. No h's on the outside. So we can literally just grab, say, the T2 estimate for that one, and I could put the T1 in for that one, make that P equal to 2, do this computation, and I just boosted my precision. So let me say this in a different way. Let me summarize it for our trapezoidal life. So if T sub k, so now think about this, T sub 1 had step size h, T sub 2 had step size h over 2. So if T sub k uses step size, it's going to be basically h over 2 to the k. Just k. Well, because this one's going to be h over, so I do need a power of
Would it
k.
be k minus 1?
Two, k minus 1, thank you. That's, yep, like that. Is that what you were saying, or?
No, but that's right.
That's okay, cool. We got there. So T sub k uses step size h over 2 to the, so this one is 2 minus 1, this one is 2 to the 3 minus 1, it's 4. So we've got this rhythm up here. We can just take this formula and crank it out. Keep in mind that P is equal to 2 for our first estimates. Then we're going to have our improved estimate. It's going to be 4 times the later, the second, the deeper estimate, so that's going to be t to the k plus 1 minus t to the k, because every time this index goes up, the step gets halved, over 3, because p is 2. That's crazy simple. You take 4 times your better estimate minus your previous estimate divided by 3. So let me put that in that kind of heuristic way. So it's 4 times improved trap minus current trap over 3. We'll come back to this. Make a little note of this because I want to come back to it in just a bit. Actually, yeah, we'll just come back to it in a second. So let's take our table, let's make a table of values. So if someone could please list off those estimates. So the T1, what was that? That first estimate, we got
1.9047. One more or less.
One more.
3.
Thank you. Cool. And then T2?
1.726. 661.
Cool. Thank you. This one, sir?
1.663532. Or 33, sorry.
That's okay.
For rounding.
That's all good. That's great. And then last one.
It's 3533.
So
1.66.
Okay.
3533.
Got it. Thank you, Lou.
Sorry.
Appreciate you. No sorries needed.
And then 1.644599.
Okay, cool. Yeah, we'll just go with that.
Well, it was 98 and then
Yeah.
so I was rounding up.
That's great. That's awesome. Okay, so now we're going to use this rhythm right here to make improved estimates. We're going to take pairs of them. So for this next one, I'm going to take 4 times this value, and I'm going to take just this value here, 4 times this minus this. So let's write that up. And you can just put the third out in front. It's going to be 1/3 of 4 times this dude minus this one. And we should get an improved estimate. So could we get that, please? I could, but then it takes me like 10 minutes just to turn on the calculator.
Do you want it?
Do you have it?
Yeah.
Awesome.
I got 1.667314.
1.667314.
Yeah.
Cool. Anybody else getting that? Let's get some sanity check. Yeah. Cool. And does everybody see how we got that? Is there any questions on how to get it? Then do the next 2. So now, just that same rhythm, these 2 and then these 2. I'm just putting them straight across. So 4 times this minus this divided by 3. 4 times this minus this divided by 3. This is the part that Dr. Gray was like, that seems unbelievable. Because these new estimates are order h to the 4th estimates. These were order h squared estimates. Yeah, do you got some more up here?
Sorry.
Oh, you got Excel.
Yeah.
You got Excel. Yeah, just go ahead. Let's go
Okay.
for it.
Yeah. So I got 1.642489.
Yeah.
And then 1.638229.
Thank you. Seem okay? Yeah. Cool. So these are order H4 estimates. We're going to Richardson extrapolate these now, but we have to change the formula. Remember how the formula worked? This is actually, let's see, let's go back to it. Put it up here. Actually, here's the kind of the general rule. Yeah, so the next one. So this, I'll just put it right here. This is going to be 2 to the 4th h over 2 minus trapezoid at h over 2 to the 4th minus 1. Remember, that was 2 squared in the last one, and that was 2 squared. So this is just that p that we had there. But now our error is order 4 So instead of using 4, we're gonna have a 16 here and then a 15 down here. So let's do this. We're gonna take 16 times this minus this divided by 15. And we'll come up with 2 new ones.
Oh, I
There you go. Have you got them? Did you work it all
did
the way
whole
out?
thing, yeah.
You did it nice. You're a little too speedy.
I know. I got too excited.
Our seminar together in spring be very, very not speedy. It's gonna be great.
Oh,
Isn't
yeah.
it?
I was like, what? RCC.
RCC.
I got it.
So Lou, what did you get?
All right. I got 1.640835. And then I got 1.638007.
Okay. What error do we have on these?
H to the 8th.
A little too speedy, just the 6th now. It's gonna be 6, because when you think about, I'm glad you actually said that. Think about how this Taylor series was gonna go. They're actually just these even powers of, and you probably don't know this, so that might be a good part of it. But the error chain goes like this, it's just even powers of H. So first one we knock this down to here, now we're gonna knock this to here, and then the 8th will be our last one. So this one here is going to be, how do we combine these? It's going to be 2 to the 6th. So, and maybe you're a little confused just because I had said something about 2 to the, or H to the 8th. That's going to be what we're left with. So the final one will be an H to the 8th, order H to the 8th estimate. So this is going to be 2 to the 6th, tk plus 1 minus previous t sub k over, what is this? That's 63? Yeah, that's 64. So give what you got, Lou.
Oh, I got 1.637962.
Okay. All right. Now, how do we know if we're right? Well, we're going to go to Wolfram. What were you going to say, Josephine?
Just check it.
Yeah, exactly. Can somebody go to Wolfram and do this integral for us, please? Or Symbolab? Have you already done that too?
I did it because I was curious.
So
I got, it says it's approximately 1.6378, so we're pretty close.
Oh, that's pretty dang good. Yeah, so this is the true value. Of course, going to Symbolab or Wolfram is faster than everything we've done here. But yes, ma'am.
How are we coming up with the general formula for its step again?
Are you talking about where I'm doing the?
Yeah.
Yeah. Let me give you the general rule here that I think will help. So, I think this will help here, Lavina. So if I want to move. Okay, I'm going to make a little table up here. Where is my little table? So, the general improvement's going to be this. It's going to be 4 to the ith t to the k plus 1. I'll explain where that I is coming from in just a minute. And then minus t to the k over 4 to the I minus 1. So what is that I? This I is the depth I am into this process. So at this point right here, this was I equals 1. This was I equals 2. And then for this last one, this was I equals 3. And 4 cubed is 64. Does that help? Mm-hmm. Okay, cool. if we wanted to get crazy, we could easily build this table up by finding t to the 8 or t5, and then just propagating those changes up the chain to get an order h to the 10th approximation. But one thing to just keep in mind and maybe make a note of is that this dude is h to the 8th. And I guess we could sit here and do another one, but that doesn't seem very good use of our time, does it?
We
Lavina
just
says.
have Lou do it.
Yeah. Yeah, we're not gonna do that to Lou. Lou's been very helpful today.
Last question.
Yes, ma'am.
If we wanna go another step, wouldn't we need like t to the 5?
Yes. Yes, exactly. Which sounds a little painful. Except I see Lou's like doing it right now, probably.
Of course.
Let's actually here, you know what the best way to do this is to use the code I wrote. Let's get the code out. So let's go to World Code. Hurry up before Lou does it and see if we can beat Lou with my code.
I doubt Reader's internet can beat
I know, I can't even get the computer on before Lou adds 3 more levels to this. So this is again I've been into the cut and paste code because I can never find a path for my Jupyter notebook and figure out where things are saved. It's just easier to cut and paste it. So there's 2 code pieces that I'd like you to look at. The first one is the trapezoidal rule. And then the other is Romberg. Oh, this process is called Romberg Integration that we just did. So if you use the Richardson extrapolation on this trapezoidal stuff, that's called Romberg Integration. See if you can first just get the trapezoidal one going. And we can even enter Daniel's function once we have a robot to do all the brutal work for us. Okay, let's see if I can not ruin this. I'm gonna try. I just seem to never learn lessons. It looks kind of messed up still.
It's still slimy.
Yeah.
What are they?
I don't think they did anything.
I think you're right. I
Classic.
Those, you know, there's like a pile of 30 projectors in the basement of Clark right
Are you serious?
I'm so serious.
What? What did they even like look at this?
No.
Probably not.
They probably looked at it and said, I don't see anything wrong, and didn't turn it on or anything. Or
Oh yeah, they like
"Oh,
looked up
fixed."
here. Yeah, it looks fine.
No, like with it turned off, they're
Oh.
just like, "Eh,
Right.
looks good enough to me.
Yeah. Ridiculous. Well, I went around this morning telling everyone that this projector was fixed.
Oh.
After guys are quite surprised.
Tell him I did it again. Just tell Cybert he did the same thing again.
Is this their quadrature?
Yes, this is under the quadrature section.
Is it recursive trapezoidal quadrature?
Yes, sir. And hopefully there's a second one that says Romberg.
Yep.
Okay, cool.
Oh, that hurts.
Your back hurts?
I did not realize you were doing.
There we go.
Wait, were you like lifting, were you like carrying bricks this weekend or something? Or doing some heavy workout?
That's true. Beer carries everywhere.
I doubt my back needs
So I think think I have my good old sine in there, my sine integral.
Yeah,
Yeah, because I just love that. But I'm putting Daniel's in.
I got mine in.
You got it in? Cool. How did it compare to our answer? Pretty good?
Let's see. It's the same thing. That we got.
Outstanding. That's so good. We did work. We did good stuff. Look at how compact that code is. It's crazy.
Just pat yourself in the back.
Yeah, absolutely. Yeah, a little bit. But it is beautiful, simple code.
Yeah.
That's all I'm saying.
Look how good that code looks.
Like, it's just so
code more beautiful than this. I
so
don't think so.
clean, so clean. I doubt anyone else would find this. But I got some cool use of, well, you know, if you could see them, I guess you can on your screen. That sum function is very nice. You can see how I kind of implemented that in a way to just quickly do those new points that we're adding in. And I'm gonna run this, okay. So NP, I think it's EXP.
Yeah,
Yeah.
it's NP.exp.
And we did 1 to 5, so I'm gonna do 1.0 to 5.0. Where B, there B function. Oh, now I'm wondering, because I used this like as a pointer. Did you just enter it with an X in there? How did you enter the function? Because I did it as a pointer.
I'm on the. This is the Romberg interpolation.
I think we
Or
could.
integration. I did it in there.
You did what?
I did it in the Romberg.
Oh, you just went straight to the Romberg one.
Yeah.
Okay. Yeah, freaking, we'll just do that.
Can't see this compact code in there.
This code will be here if you need it, and you will need it at some point.
I can try it with the other one.
Yeah, give it a shot, because the way I put that function in is not standard function implementation. Romberg's going straight first. Yeah, and then this is classic here. I just use lambda notation, which I know how to tweak. So I'm sure numpy is just exp. Is that what you did there, Daniel? Yeah.
Yeah.
In np.exp. Cool. Where was, so when you did your function, it was x minus 1 for the exponent on top, right?
Yeah.
Okay, thank you. That, yeah.
Makes sense in the parentheses.
Yeah, it feels like I am. Yes, you are correct. I'm just going to get rid of that first one. There we go. And then our interval is 0 to 5. Or 1 to 5. Cool. And so the K is basically the depth of your table. And we did a table of depth 4 by hand. But if I wanted to add that extra bit, like I was goading Lou to do, we could, look at that. It's so much easier to make these tables print on a lower diagonal as well. But here we can really see things settling in to this 1.637 just settling in the whole way. But if I want to go to like, how many, what should a K, how many rows should we do?
50. Do crazy.
Okay, no, how about we just start with like 10 and see what happens, because I'm afraid things, oh my goodness.
I'm gonna do 50. It's really close.
Same thing.
So you can actually see that it was way overkill because none of these values change anymore. The precision has become so great that we need more decimal places to show it. So let's see, we can improve the decimal places. And you can see that, I don't know what line number this is, but see that 8F? We can
Slow
just
down.
change that to like 12 decimal places of accuracy, and then over here at 1, 2, 3, 4. That should
It's like
make
running
things better.
simulation.
The window's too dang small, even.
Can you make it big?
Can I?
No, I don't think so.
Doesn't seem like it, does it? Wouldn't that be horrible to do it by hand?
Yeah.
I can't even see where, I guess this final number down here is our final answer, this 1 point, this guy right at the bottom down here. Oh, it gives us, that's right. It summarizes. So, anyway.
And 50 is still running.
Is it, did you put 50?
It's taking forever.
How long does 20
take an output? I don't know. This
Oh,
was-
boy, that is, I see, 20 takes a while.
Still going. Yeah, it's
Still going, dang, okay, well, we'll just
Very
maybe,
curious.
you can email us all when you get a final answer. Alrighty, friends, I don't have any assignments for you today, but the next one will be on this stuff. If you want to read ahead, read about Gaussian integration in the book. This is a whole different method. So Gaussian integration is almost pure mysticism as to how it works. The key is there's this thing called Gauss nodes. I'll just give you this. So actually, please read this before Monday. It's just going to make it so much easier. There are specific places where we can evaluate a function to get its integral just by evaluating the function at these points and adding them up. And that's what the Gauss nodes are, and we'll talk more about it, but it's utter magic. So thank you. I will not see you Wednesday morning. I will record, actually I'll probably record a little lecture on Gaussian integration so that we're kind of warmed up for Monday. And then Daniel, you'll totally watch that before class, right?
Yeah.
Oh, can I have a calculator?
Yes, sir.
Oh.
Thank you.